There we go. All right. I mean it this time. I'll begin. Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to guide our steps today. Help us to glorify you what we do and to understand a little bit more about energy. In your name I pray, Lord Jesus. Amen. All right, so it was pointed out to me that I have not talked about power yet, and shame on me. So the shame on me, that I'm adding that. That was not added by the student. The student's more polite than that. But I should talk about power, so let's do that. It's not that complicated, really. We can ask, what's the power developed by a force? And so here's the deal. Power developed by F at time t is, forget the time t. Let's just say the power developed by F is the force dot the velocity. All right, this is a formula for power. No, so like, if you think about this, the work, right? If we think about the work done at time t, and suppose we're talking about this integral, I'll call it c sub t of f dot dr. And so here I'm saying integral, say from t naught to t. I'm thinking of t as the fixed time, just to draw a picture here. So we've got some curve that begins at r of t naught, right? And it ends up here at this point at r of t, right? Then we can ask, what's the rate of change of work that's being done by this force at this time t, right? That would be the power. So we know how to calculate the work at time t. It's simply, we take f, right, of r of t. I shouldn't use t here because t has a different meaning. We use tau, r of tau dot dr d tau, right, integrated over tau. That gives me the work at time t. So what happens when you differentiate that formula? Did I mention that I dislike this room? Boy. Oh. Apparently there's some kind of party going on over there in the history department. What's that? Do they have food? They might. I don't know. You can go over.
Should we take a field trip?
If you want to, I won't stop you. But I'm going to keep talking though. So if we differentiate this, right? What's this tell us? dw dt is what? If I differentiate this integral, what happens? You just get f of r of t dot dr dt, right? In other words, the force dot the velocity, right? Now, in context, it's the force dot the velocity at the time that's in question, but that's it. Yep. Yes, sir?
Did the tau become t when you differentiate?
So what I'm using the fundamental theorem of calculus part 1, right? Remember this thing, like d dx of integral from like a to x of f of t dt? Remember this thing? So when we differentiate an integral with a variable bound, we just get the integrand at that variable bound.
Right. In the first one, it's f of r of tau, but in the second one, it became f of r of t.
Yes, that's on purpose. So this right here is playing the role of like the integrand at g of tau. And so like if I have d dt of the integral from t naught to t of g of tau d tau, by the fundamental theorem of calculus part 1, this is g of t. But g of t is the force evaluated at the path at time t, time dot product with the velocity. So this is why the formula for power is force dot velocity. Another way of looking at this is when we calculate work, what are we doing? We're integrating the power, right? The integral of power, the integral of the work per unit time with respect to time gives me the net work done by that force in question. So to give a more specific, so here's a silly example. I'll start with a silly example. Find power due to tension force. And so here we go. We'll put a cat in the bucket, and let's suppose that the cat is being swung in a circle by a robot monkey not pictured. All right. So this cat is being, swung in a circle like that, right? So my question is, when is the power due to the tension force largest? When is the power due to the tension force smallest? The power developed on the tension force, by the tension force on this cat in motion.
Is this horizontally or vertically?
Well, you want me to draw the tension force?
Well, what I mean is, like,
I can do that.
is gravity playing?
Oh yeah, this is, I guess it doesn't matter. This could be in space. I'm only interested in the tension force. So you could think of this as a horizontal thing, like one of those, spin the cat against the back wall of the amusement park thing, like that. Or we could think of it as like a vertical kind of, put a cat in a bucket and like that kind of thing. Either which way. So what's the power developed by the tension? I'll draw the tension force. The tension force is along the this right here, right? There's the tension force. So what's the power developed by the tension force? Where do you guys think it's largest? At the top or the bottom? Bottom? How many for the top? It's a trap. It's all the same. What is the power developed by the tension force? Where's the velocity? Where's the velocity point in circular motion, guys? Like these, right? So you got tension up here. Again, the velocity is like this. The tension force is center seeking, yes? So in this very silly example, the tension force dot the velocity is equal to 0. So the answer to my silly question is the power is 0. Corresponding to the fact I said early on that the work done by a force which is perpendicular to the motion, the work is what? The work is 0. Right? Well, the power is also 0. Let me do a more interesting one. This was a silly question. Here's another one. Example 2.
Why does that make sense? Like, you're proving it mathematically, but why would that make sense logically? Because there's definitely some force, some work at play in space.
Yeah. But it's not the tension force. Like, you can't make the cat go in a circle with that. To get it going in a circle, I can pull, if I had something to hold on to, like, if I had a yo-yo, right, and I was holding it like this, it doesn't matter how hard I pull it this way, it's not going to make it go that way. So the circular motion that you're thinking about, that is due to something else other than the tension force. There has to be some sort of it has to be some sort of tangential force to get that going, right? So the devil's in the details of this, if you actually have a yo-yo and you try to spin it, you actually have to move your hand a little bit. Anyway, it would be complicated to explain all the details there, I think. I'm not sure I could right off the cuff like this, but so there's a separate question of how does the motion start versus how the motion, I'm asking a very specific question, which is what's the power due to the tension force? Since it's perpendicular, we're stuck with this, but indeed there are whole videos on YouTube devoted to this is wrong because it's moving. And some of those people are professional physicists, so whatever. But it is nevertheless the fact that the tension force here does 0 work. Okay, so a more interesting example perhaps, we could say, I don't know, all right, I'm not sure this is more interesting, but it's an example. So suppose your force is I don't know, 10 newtons minus 2 newtons, 3 newtons. And we go from, well, let's suppose that we're at the speed, the velocity is, let's say, this is a very simple example, 3 meters per second, 1 meters per second, and, I don't know, 7 meters per second. All right, what's the power developed by force in this case? This is pretty much the simplest power question I can ask that's not one-dimensional. I guess the one-dimensional questions could be easier. So the power, again, is F dot V. So I just have to take the dot product of these two vectors, and I get, what's the dot product here? I get 30 minus 2 plus 21 Newton meters over second. So does that make Newton meter over second? Can we rewrite that? Let's see here. I heard a watt. What's a watt? What's a watt? I'm sorry, that's horrible. 31 minus 2. I think we got a 49. So this is a 49. A Newton meter is a joule, right? So this is 49 joules per second. But indeed, as you guys have told me, we call that a watt. The big W is for watt, in honor of some dude named Watt who did stuff on this early on. Yeah. So a watt is a joule per second. Joule. Do you guys know what the funniest sounding unit is? At least according to my sister-in-law. For some reason she finds this very, very amusing. I don't quite understand it. It's really from next semester, so I'm ruining it, but since most of you won't be with me next semester, since next semester I'm teaching the junior level class, which is not the one after this one. In my sister-in-law Jessica's opinion, H is the most funny unit because H is for Henry. I don't know why, but that's, I might be spelling that wrong, but Henry, yeah. That's the unit of, oh goodness, what is that a unit of? I think inductance. Oh no, maybe I shouldn't teach physics too. That's not good. All right, let me erase the evidence here. Any questions? So this one's relatively simple. We can ask other questions like, example 3, suppose you've got a mass, right, and it goes up, and then it comes back down, right? And we can suppose it goes up with speed v naught, like that. We can ask, what's the power developed by gravity during this motion, right? So what's the power? Power going up is what? The force of gravity, right?
Is this straight up or at an angle?
I mean it to be straight up. I'm not good at drawing straight up. So the force of gravity dot the velocity, right? So the power going up, what's the situation here? Going up, we've got a velocity that's this way, right? But gravity is that way, right? So the dot product is just what? Minus what? Minus mg v, right? Is this constant? Is the power constant? I mean, the force of gravity is constant. Is the power constant? That's v at time t, right? I'm talking about the power up at time t. What is this actually? What's the formula for v? The formula for v is what? V naught? What? Minus what? Nobody knows? No one knows how to find the velocity as a function of time in this situation? Initial velocity is v naught. Earth, gravity. Come on, you guys know this. Minus gt, right? This gives me the velocity at time t, right? So, I mean, that's technically the formula for power. So what's the power being developed by gravity right at the zenith of the flight? Power is 0, right? Because the motion stops. The velocity's 0 at the very top, right? The power developed by gravity is largest at the bottom, right? And how about the power going down due to gravity? There we have the different situation, right? There we have mg aligned with v, right? So in this case, the power is positive, I think. So we've got mg. And I got to be careful here. Rats.
The negatives cancel out.
Yeah, the negatives cancel out, but I gotta be careful with my.
GT overcoming V naught.
Yeah, I think so. I technically I've got to put a minus v here, and the reason for that is that since v is negative, because it's falling, minus v is actually positive. So the formula here is actually mg, and it's still this formula. The velocity is still v naught minus gt, right? I think if I'm sorry, I've ignored my minus, right? I'm sorry, what did you say?
Would the mg not be negative like it was in the first equation?
I just, say what you said again, I'm sorry.
Would the mg not be negative like it was in the power?
Well, mg is always downward, but the thing is with the v, on the way up, v is positive. So, the dot product is definitely should be negative because they're opposite directions. And just from a more intuitive perspective, the power is negative due to gravity because it's taking away kinetic energy as it goes up, right? So like the work done by gravity is negative in the upward motion. But the work done by gravity is positive as it's falling back down. The change in kinetic energy on the way back down is positive. The change in kinetic energy on the way up is negative. We can always think about work energy theorem. What I'm saying is if my formulas are correct, this should be less than 0, and this should be greater than 0. The issue, though, is that I guess to be specific, what's the time to the time? What's the time here? What's the top time? We do what? We do. Second here, right? We have 0 is equal to v naught, right? Minus gt top, right? That's the time. That's the formula that defines the top of the flight. So the top of the flight is v naught over g, I believe. You know. So to be fussy, this is only true for 0 less than or equal to t less than or equal to time v naught over g, whereas this second case is for v naught over g less than or equal to t less than or equal to, when does it come back down to where it started? Let's assume it's been thrown from the ground just to make things relatively simple. What's that? Yeah, 2 v naught over g, right? That's how much time. So we could graph the power as a function of time, and maybe that would bring more understanding to what's going on to this problem, perhaps, you know? So like, let's try that. What's the graph look like here of power? Let's see here. So suppose that's v naught over t. It starts out at, where does it start out? It starts out at, I plug t equal to 0, it starts out at minus mg v naught, right? That's the initial power. Force of gravity times the initial velocity. And it's negative because, again, they're opposite directions, right? Now, what's the, so this is at v naught over g. Over here, at 2 v naught over g, what's the power? Right before it hits the ground, what's the power by gravity? So we've got the mass here, the velocity is v naught in the opposite direction, right? So the power is positive due to gravity there. I'm talking about power for gravity. And so it's the same thing, but positive, right? And I think, dude, that's the same formula, isn't it? I think it's just this, isn't it? Yeah, duh. I'm a dummy, you guys. Look, we don't need to do case-wise analysis here. I'm sorry. Check this out, right? The power at time t is what? Is the force of gravity dotted with the velocity. Let's write these as vectors. 0 minus mg, right? What's the velocity? It's 0, comma, what's the formula for the velocity, which holds over the whole motion? Is just what? V naught minus gt, right? And so that is equal to gt minus v naught times mg. Or if you like, well, anyway, that's the formula. I'm not sure simplifying it really helps any. Right. So does this make sense if you think about it all together? Remember that the integral of the power over time is the work done, right? So we've got negative work done by gravity here. Then we have positive work of gravity done over here. They're equal and opposite, so they cancel out. The work done by gravity over the totality of the motion is 0 because the change in kinetic energy is 0, right? Is it the same situation before and after the throw, though? Certainly not, right? At the start, it's going up with velocity v naught. At the end, it's going down with velocity v naught. So something certainly changed in the throw, just not the kinetic energy, because the kinetic energy before and after is equal. To understand the difference before and after, we need some other concept, namely momentum, but that's after test 2, all right? We can argue, in fact, the change in momentum in this problem is non-zero. But I'm getting ahead of the story there. Any questions? So sorry, I mean, I don't think I really needed to divide into cases because I could have just done this calculation once and for all, right? So. Any questions? No? All right. So let me work another example for you guys. Let's see here. I can find my thing. So if a force is going in the direction of the motion, it should be developing a positive power. If the force is going opposite the direction of motion, it should be developing a negative power. If, on the other hand, the force is perpendicular to the motion, we get 0 power, like in my silly tension example. And if we integrate the power, that gets us the work done by that specific force. So example 4 here, I'm going to go back to a one-dimensional example for a second here. Let's suppose yeah, particle mass m is undergoing one-dimensional motion with force of applied as a function of x, and it's equal to, let's say, alpha x cubed minus beta, I don't know, what do you guys want, x squared? We'll put a squared here. That's probably good enough. I want something that involves a little bit of calculus, but not too much, all right? So I think this is a good, it's a good fit for us at the moment. And so that's a variable force, right? The variable force. And the question I want to ask is, let's see if I can come up with a good question here. If, let's say the alpha is equal to 4, beta is equal to 3, and m is equal to 1. And let's see here. If I make the units reasonable, what should the units be respectively? If alpha is going to be a meaningful constant here, I have what? I need to get a Newton coming out, right? I would need what? I would need like newtons over what? What? If I got alpha x cubed, I want it to work out to a Newton, I better put a meter cubed down here, right? To make this be dimensionally meaningful, I would need beta to have units of newtons over meters squared. And, well, m better be kilograms, right? Okay. All right. Suppose that's the situation. If the initial velocity is 10 meters per second, then find the final velocity when the final x is equal to, let's say, oh, I don't know, 1 meter, given, let me make that 2 meters, actually, guys. Given that the initial position is equal to 1 meter, right? Actually, let me change the question just a little bit. If V naught is equal to this, and Vf is equal to 20 meters per second, when xf is equal to that, and x naught is equal to that, then is F the net force? There we go. This is a more intelligent question for us. It's not just a rote calculation. Okay, so how do we judge whether or not a force is the net force? Like, what does the net force do with respect to energy? It does what? It satisfies the work-energy theorem, right? So if it is the net force, we should expect what? This would say what? This would say that the work done by F should be equal to the change in kinetic energy. So we can calculate the change in kinetic energy for this problem from the outset. We have all the information we need to figure that out, right? So given this right here, what's the change in kinetic energy? Well, change in kinetic energy, 1/2 mvf squared minus 1/2 mv naught squared, right? So let's see here. My mass was 1 kilogram apparently. I always regret not making my mass 2 kilograms to make that half go away, but it's too late. I've done what I've done. So 1/2 and 20 meters per second. I'm gonna put the units out front here. 1/2 times 20 squared minus 1/2 times 10 squared The units on all this is, of course, joules. And what do I get? I got like 400 minus 100 is 300. 300 over 2 is what? 150 joules, right? All right. So if, in fact, this force is the net force, the change in kinetic energy should be the work done, and that work done should be 150 joules. What is the work done by this force, though? How do we calculate that? What is actually the work done by this force? Is the following. So W sub F is equal to the integral from 1 to 2. And I'm going to omit units if you guys don't mind. But I'm working in kilograms, meters, and seconds, all right? So the integral from 1 to 2, alpha was what? I've got a 4x cubed minus 3x squared dx, right? In one dimension, we just integrate the force, right? We don't have to take the dot product with the velocity because of the one-dimensional aspect of the problem. In my notes, I work out why that is. Like, it's just basically a U substitution thing. But there it is. I mean, we just have to do this integral, which we can do, right? What's the antiderivative here? I think we got x to the 4th minus x cubed. Take that thing, evaluate it from 1 to 2. What you got? 16 minus 8, parentheses, minus 1 minus 1, also known as 8 joules, right? So is this the net force? The answer is a resounding no. This is not the net force. Something else is at play here, right? I can't achieve this motion with just this force. There has to be another force at play, right? If the other force was a constant force, what would that constant force be? So here's a follow-up question. If F net is equal to a constant force F naught plus the given force, which is a function of x, right? Then what is F naught? So what's the work done by the constant force F naught in this motion? See, because there's an additivity here, all right, guys? The work done by the net force is equal to the work done by the constant force F naught plus the work done by the force I'm just calling F. We just calculated the work done by the force F is 8, right? So we know that this, by our kinetic energy calculation, is 150 joules. We just figured out that this is 8 joules. So what does the work have to be done by the... Yes, is there a question? No? Okay. So this tells me that the work done by the constant force apparently must be what? I think 142? Hey, if I've made a typo somewhere, let me know about it now before I go any further. No? Okay. What's the work done by a constant force, though? Is which direction is the constant force directed, right? Like, here's a picture of the situation. We're starting out at x naught equal to, what was it, 1 meter? We're ending over here at xf equals to 2 meters, right? So we're moving rightward. The constant force is doing positive work. It must be directed in the same direction, right? So if I were to draw the constant force, it should look like what? I think it should look like this, right? And so what's the formula for the work done by the constant force? It's just what? F naught times the change in x, right? Force times distance. It's that basic middle school physics thing. I'm sorry, I live in a world where middle schoolers take physics. It's not a world that many people live in, but that's the world I dream of. What can I tell you? So F naught, we all have different dreams. Delta X is what? Oh, 1 meter. Oh. So 142 newtons, apparently. There you go. It would take a constant force of 142 newtons as it happens here. Right? So you see we can play these games with this. We can talk about, here's a situation. I give you a partial description of the forces in play. You can calculate the work done by each of the forces that are described. And if I give you enough information about the net change in kinetic energy, you can kind of piece together missing things on the basis of what you understand, right? And this kind of thing can be used to analyze actual physical situations where you have like understanding of certain parts of the situation. Like you understand the work done by certain forces, but maybe there's another force that you don't have a clear description of. It could be like something very macroscopic, like the force of friction during a crash or something, right? So you can kind of work backwards from the kinematics to figure out net works done by other forces in this way. All right, so there's an example for you. Any questions? I'll come up with another example. How about example 4? If we calculated the work done by the force, and so I just calculated the work done by the force by integration. What's the other way we could have done it? Is f of x here a conservative force? How about this? After I've got done completely describing the question, the net force is what? Let me write it down. So example 4 continued. We have the net force is what? It's equal to 142 plus apparently 4x cubed, right? Minus 3x squared, right? In kilograms, meters, seconds, etc., right? So like the force, I'm omitting units, but it's in newtons, obviously, right? Okay. Is that a conservative force? What do you guys think? We've spent a lot of time talking about conservative forces in 2 dimensions or 3 dimensions, but we should also talk about the problem of deciding whether or not a force is conservative in 1 dimension, right? Can you give me an example of a force in 1 dimension which is not conservative? There's one that comes to mind for me immediately, which is friction, right? If I just think about friction in a 1-dimensional setting, that's not a conservative force, right? It depends on the path. The energy I lose to friction, I can't get back, at least with current technology, probably ever. Is this conservative? It just begs the question, can I calculate a potential energy function to it, right? So in 1 dimension, this is the gradient, minus the gradient of u in 1 dimension. In 1 dimension, the gradient is just the derivative. So, like, the force being conservative just becomes the question, can you calculate an antiderivative? So can you calculate an antiderivative of this? Yes, you can. I'm not going to give you the option not to. Yes, you can. We all can do that. Minus 142x minus x to the power 4 plus x cubed, right? There you go. That's a formula for the potential energy of this system. If you differentiate that, we get what? Minus 142 minus 4x cubed plus 3x squared multiplied by minus 1, we get back the force. It checks, right? So what was the work done in the last problem? What was the work done going from x equals 1 to x equals to 2? Well, it was the change in kinetic energy, right? But it's also minus the change in the potential energy, which we can double check our work. I think it's fun to do this. So we're going to take minus u of 2 minus u of 1, right? Which in this context is, let's just write it u of 1 minus u of 2 because that's like not as annoying. And so that's what? That's minus 142 minus 1 plus 1 minus parentheses minus 142 times 2 minus 2 to the fourth is 16, right? Plus 8. So how does that work out? We've got, what, minus 142 plus 2 times 142, I think plus 8, because I get like a minus 8 times a minus, which gives me a plus 8. So lo and behold, we got 150, right? As we must, because that was the change in the kinetic energy. So all these things work together. Question, what's the power developed by f of x during this motion?